Okay, so finally we get the hard problem, and now it's not 11 p.m, so maybe I will solve this and go to sleep sooner than midnight. Number of good subsets. You are given an integer array nums. We call a subset of nums good if its product can be represented as a product of one or more distinct prime numbers. Good if its product can be represented as a dot product of one or more distinct prime numbers. So that means either it's the prime number or there is one and some prime numbers. Okay, so are the values unique themselves? We know what a subset is. Okay. Yeah, it's not written there. Distinct prime numbers. Subset of num is any array that what is that? So they don't have to be unique. Okay, so they don't have to be unique, and they are quite small, up to 30, which makes sense, because if you multiply all the numbers, then if its product can be represented as a product of one or more distinct prime numbers. Okay, so the numbers are quite small. So what we need is that in the subset, if we decompose the numbers, right? So because let's say we make a product of 4 and 15, right? So the product is made up of prime numbers, of which are 4 and 15 made up, so 2, 2, 3, 5. So since the numbers are 30, we can easily do it in we don't even have to use anything smart. We just compute prime numbers that are smaller than or equal to 30. And now, there is actually not that many of them. I have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. So there's 10 of them only. Okay, so brute force solution. Let's try all numbers, all subsets, and then for each subset we just evaluate. And how we evaluate, we need to do a prime decomposition of each of the elements and see if they are unique. All the prime numbers. So first, okay, now how can we speed this up? Let's say, first of all, we are doing the calculation for, if we decompose, no, not really. Basically, let's say we create a mask. So there is 1 in the mask of the number if it has the in its prime decomposition is number 2, then if in its prime decomposition is number 3, and so on and so forth. Now, oh, sorry. To evaluate, so for each number we just find out its prime numbers that divided, there's 10 of them, so we just do O1 work for each number, we just check if it's divisible by each of them. And now we wanna do a end of all the masks, and if there is no intersection, we are done. We also need to check if, for example, 4 is not a good number because by itself it already consists of 2 prime numbers, so they are not distinct, so 4 is not in any subset. So what I am thinking is that instead of doing it for all, because if we evaluate, if we take subset which is 1, 2, and then 3, and then 1, 2, and 4, we are absolutely uselessly evaluating this. Like absolutely uselessly. And this, first of all, has to be a good subarray, so we could do some pruning in the backtracking, but... So let's say that we are at number 15 here. And we want to count, so let's say we want to count the subsets which are composed of these all numbers, including 15. Well, what can those subsets be? Those are good subsets here. So the number of good subsets here, which do not contain the prime numbers from here. So, for each position, we can compute the number of subsets from first I elements which have some exact, like we could keep the mask of prime numbers. So we say, okay, how many subsets are there from first I elements that have these prime numbers? And actually, the subsets can have at most 10 numbers, which I don't know how that helps us, but okay. So now what are the transitions? Let's say if we check, for example, how many subsets does okay, so how many subsets are there from these numbers that have, like, I don't know, 2, 3, 5? Well, that is the number of subsets of these elements that have 2, because 3 and 5 is here. And that's the whole logic, that's the whole thing. And we only check the masks which have the prime numbers from here, and we just copy the previous. We don't add anything extra to the previous answer if this is not even a good number. If it already has 2 equal primes, then we don't do anything. So let's start with coding. Okay, so I'm not sure if I should say that it's been only 10 minutes. I'm not sure if I'm supposed to explain the time and space, but let's say I can. At each position, we consider all the masks, and there is only one state from which we can get to the mask. Or is it? I think yeah. So for each position we go through all masks. There is 1024 masks and there is n positions, so it's 2 n times 2 to the p, where p is the number of distinct prime numbers here. And space complexity, what we can see that values for I only depend on values for I minus 1, so our memory is only 2 to p. So const int p is 10, const int primes of length p is equal to 2, 3, 5, 7, 11, 13. Okay, let's not make it const. I mean, it won't change, so it can be const, I guess. 17, 19, 23, and 29, I think are primes. And I think there should be 10 of them. Yeah. So, let's grab the size of the nums. Now let's make a vector int dp of 1 to p. So this is the initial number of subsets. There is 0 subsets of 0 elements whose product is a product of one or more distinct prime numbers. Okay, and now we go through nums. Okay, and what we do? dp, and we go through all masks. So for int mask, first we calculate its mask. So int current mask for int prime number for int primes and now if let's save number, so nums I. Okay, and now nums while prime percentage of the count, or we don't actually have to do this. If num percentage prime is 0, if num percentage prime is 0, then num divide num by prime, and then current mask or it with 1 to prime. I have no, I need to index the primes, so int j under p j plus plus, and let's int prime is equal to primes j, so 1 to j. And if after dividing the number is still divisible by it, then we say current mask is -1 and we break. Now if current mask -1, we just continue, we just copy the array, right? Now if we make mdp, so vector int mdp 1 to p. We now go through all the masks, mask another 1 to p, mask plus plus, Okay, so we go through all the masks and NDP. Now, if it's a good question. If we are overlapping, so we are there. Otherwise, it should be the same, I think. Because how many ways from first I can we do with some subset of primes which is not matching the primes we have here? So let's say this is like 3, 5 and we are on mask 2, 3. Well, we can't make it. So it's the same number of, so we can do here, so NDP should actually be equal to DP. And then if mask and current mask is equal to current mask, and this needs to be in brackets, then we do NDP current mask plus equal, no, is equal to DP current mask plus DP current mask XOR mask. So we want to turn off the bits that are in the current mask. Okay, and we modulate. And I think I should use long, and let's make a const long mod equal to 1 plus 7. And DP swap NDP, I think that should work, or something like that. Or we can just use swap DP NDP. Okay, and then finally we just return the sum of them, I guess. So long ans for auto x in an, no, ans, no, GP, in GP ans equals ans plus x percentage mod return ans. Might work, I'm not sure. Output is 0. Okay, that's interesting. No, there is actually one way to make subarray from 0 elements. Shouldn't it all be 1 actually? What is annoying me? Oh. Ah. Okay. GP0, 1. Maybe. Okay, that didn't work. Okay. Well, okay, let's see how my algorithm will stack up on this. So, what happens for 1? Actually, let's print it. Just let's print it. For auto x in NDP, sort x, sort this. So let's see what. Okay, I don't want that. In the J, 0J is under. Well, we can have prime numbers 2, 3, so only first 2, so let's do first 10 elements. What they are. NDP J should work fine. 0. Interesting. DP0, 1. So let's check current mask. Current mask should be 0, 1, 2. Wait. Yeah, okay, 4 is skipped. That's fair. but 4 actually shouldn't be skipped. Or should it? I mean, we don't have to skip it, I guess, because there's just not gonna be, this just not gonna work, so I guess we can skip, but it's unless, I guess we can skip. Okay, so for 1 we go through all masks, and then so the numbers in this can be made up of how many unique? 2 times 3 times 5, so only 3 prime numbers it can be made up of. This is number of sequences we can make, so the current mask is 0. So this correctly solves it, I think. So if mask and the 0 and 0 is 0, then ngp current mask, which is 0, plus equals dp current mask, and if you XOR by that, that's just, you add 0 there, which is not good, I think. So I guess you go, no. That is interesting. So mask and surmask equals surmask. It's hard to speak about hard problem, to be honest, but fair enough, I guess. Yeah, it's just day 11. It's good that I can even solve it. Well, 0 should be an edge case. If there is no, if it's 1. If it's 1, then you can also skip. So let's make it like that, I guess. Whatever. That it's absolutely useless to write out. Okay, so 1. And now NDP so current mask, so the mask, so surmask mask. So current mask is, okay, that's way too many numbers. That's way too many numbers, so let's make it until 10 for now. So how many ways can we make up? Okay, so current mask is 1, that's fair. 3, this, 7, 9. Okay, it says 0. So NDP of current mask should equal to, oh my days, I am so dumb. I'm so dumb. Okay, so this is 4. Okay, so let's make it 1 to p. Still not works. Okay, so let's make this like that. Okay, now it's 8 because it doubled for some reason. Wait, why is it current mask? No, mask is equal to NDP mask, and mask, sorry if your ears died, my fiance always complaining complaining about how loud is it. So now there is only a single problem. I could do this, so int old mask, current mask, and I guess if old mask doesn't equal new mask, then like this, maybe. No, mask. So it's just for it's missing some options. Let's calculate it. So after 1, well, from 1 we cannot actually do it. From 1 there is one way to make a sequence of which has no prime. It's weird, bro. The ones are making a lot of problems. There is well, there should be 2 ways, because you can either don't add anything or add anything. So then there is 2 ways of making there should be always just one way. It's what? So what if current mask is 0? So that's only case for 1. Everything else is divisible into primes. So if it's 1, what to do if it's 1? Well, how many ways you can make subsets from these elements with this? So okay, let's say 1 is here, and now we have how many ways we can make how many good subarrays we can produce from this with some pattern. Now if we add 1 in there, well, then suddenly we have 2 ways. We can either include the 1 or not include the 1. So if it's 1, you just multiply the previous. So if current mask is 0, then oh my days, what the hell? For int x in NDP, x shift by 1, maybe. Okay, so you can't bind long into int, that's fair. So 2 ways. Now how many ways we can make a subarray which will have 0, 0, 0, 0. It's 12. Ooh. Okay, so let's break here, or continue, or let's just do this. Let's do this. So 2 in the first one. So there are 2 ways we can make good subray with 0. What? Okay, that is weird, bro. 2000 is gonna be a lot, dude. The one is making me a lot of problems. So let's say we get to 2. How many ways? Okay, and then you sum everything from... Okay, maybe that will work. I have no clue. I is under, I don't know, what, P, like that, something like that, maybe. What? DPI. No way both worked. No way. Okay, I'm not that stupid at least. Okay, so maybe I can actually skip this. Yeah, I can skip. Okay. Okay, it's not that difficult. Time limit exceeded. Okay, well, it's not fast enough, I guess, on 2 test cases only. Yeah, that sucks. That sucks. But maybe, I'm not sure which will be faster, and I don't want to run it 10 times so that it passes. So maybe if I can maybe do this decomposition faster. I'm not sure that will work. Nah, that will not work. Okay. Okay, let's use the test case and let's see what the runtime of it. It still is. No, it doesn't. It runs in 315 milliseconds. But Leetcode just sums, I think, the executions of the test cases. So that sucks. There's 11. We made out of 2 and 11. 13. So if it's made out of 17, it can only be 17. Actually, I should just store all the numbers and for all of them, because why do this decomposition? There are 30 values and only few numbers that are made out of unique prime numbers. So how I will speed this up is that instead of computing all the primes, because who needs that, question is, do I even have to do that? I think I don't need to do a new DP actually. I can maybe do it in place. Yeah! Okay, that's it. Okay, I don't have to do anything. Okay, I'm at the very end. It beats nobody. It's slow extremely. But it works. It works. Who cares? I abuse the numbers are small. So let's take a look at the actual solution. There is no editorial available. Okay. We take them. Okay. Okay. Create bitmasks for them. That's a good trick. That's a good trick. So he's doing what I'm doing. But so what wait. Already booked primes. Okay. Number we are processing. We just okay. What if we not a bad list? Numbers which divided by square. Also, we need to be sure that mask that the places we need to book are still available. Finally, how many options? Well, it's just sort that times count number. What? Oh, he's doing compression, but that's useless. Wait, that's actually gonna be faster than mine by a lot. Oh, okay, that's interesting. That's interesting. I mean, it's probably too late for me to find out optimization like that, but I mean, 91 milliseconds, it's not that bad, I think. That's fine, I guess. This is total runtime, but I mean, they have total runtime of 0 milliseconds, so, or whatever, most are under 10. I mean, I guess I could do better, but who cares? I'm going to sleep, so let's make it, I don't know, subset dp. Okay, so we cannot use numbers. Okay, so numbers with non-distinct prime factors cannot be in a good subset. So that was the first observation. So the numbers are small, and numbers with non-distinct cannot be taken. Numbers with non-distinct numbers are small, and numbers with non-distinct prime factors cannot. Few observations. The numbers are small. 130. Okay, and prime factors of numbers in a good subset are distinct. Approach. Use dynamic programming on first iterance. Approach. DPI mask is the number of good subsets from first I elements number of good subsets from the first element whose product is equal to the product we have only 10 prime numbers from 1 to 30. That's intuition. Now approach. We have only 10 prime numbers from 1 to 30. Only 10 prime numbers from 1 to 30. For each position we find the good subsets from first I elements from each position. For each position I we find the good subsets from first I elements that whose product is made up of a subset of the 10 primes, maybe. Okay, we encode the subsets of primes with a bit mask, e.g. 0011000100 corresponds to a subset with product 2, 3, 5 times 7 times 17 times 19 equals to, I have no clue what, and that actually cannot work. So 5 times 7 also cannot work. Okay. 5 times 7. Some of those masks are not even possible actually. It's like pre-filtered masks, I guess. That's a good observation. Okay, so we don't have to go through all masks, first of all, because not all, we can't have 5, 7, that's already 35. No, that's not, okay, forgot that, so that is 35. Let dpi mask be the number of good subsets from first I elements whose product is equal to the product of the primes that make up the mask. At each, let's do like that. At each position okay, so at each position something, I don't know, at each position we can either include, at each position we iterate over all masks, and we can either add the current number to all subsets This is so hard to explain, or I'm just very tired. But I know what I'm doing, I just cannot speak it, and I'm doing this for 45 minutes. That's terrible. We iterate over all masks, so we can either add the current number to all subsets. Right? Yeah. All masks, and we can either add the current number to all subsets. No, we can either we iterate over all masks, and we have two cases. The prime factors of the current number are not in the prime subset defined by the mask, in which case the number of ways to make number of good subsets of first I elements for that mask is just dpi minus 1 mask. The prime second case, the mask of prime factors of current number all prime factors of the current number are in the prime subset defined by the mask, in which case the number of good subsets of first I elements for that mask is just dpi minus 1 mask XOR current mask, where current mask is the mask of prime numbers. Where prime number is the mask of prime numbers, prime factors of the current number. The logic behind dpi minus 1 is just dp plus dp mask the logic behind dp cur mask and cur mask the logic behind is that the logic behind lies in one of the observations boom. Note that we also have to add dpi minus 1 mask, since we can always not take the current number even if its prime factor mask is even if its prime factors are a subset of prime factors of something, are a subset of prime factors of even if its prime factors are a subset of prime factors of mask. Time complexity O of n c dot 2 to the power of 10. Okay, since for each of the ON elements we go through all masks and do O1 for each of them. Okay, O of 2 to 10. Of course, a latex moment. Since we only need the previous since we only need dpi minus 1 to compute dpi, so we don't have to keep dpi minus 2, dpi minus 3, and so on. Blah blah blah. I don't know why I'm using LaTeX for the dpi, but sure. Remark: after reading other solutions, we can note that the numbers can be quite small. Numbers are small, so we can speed this up to 30 O of 30 c dot 2 to 10 by abusing the fact that the numbers are small, so we can just keep counts. We can just keep a set of them and their counts and multiply each addition, multiply each transition by the count of the current number, but I only found out about this by reading the note that remark 1, remark 2. Note that we do not have to do this. No, okay, I just, bro, 1 hour, all my days, my brain is cooked. Note that we do not have to keep two separate arrays. Oh, the answer is then sum of dp and 1, since if we don't take since a subset of 0 primes has a product of 1, which is not a prime, so we cannot, so good, so empty subsets are not good. Fair enough. Arrays for previous for dpi minus 1 and dpi minus 1 and dpi, but we can just recalculate in place. Remark 2. Note that we can speed this solution up to by abusing that the numbers are small, so we can just keep a set of them and their counts and multiply each transition by the count of the current number, but I only found out about this improvement after passing with the solution described and looking at the discussion post. And I'm going to sleep, bro. I am waking up tomorrow for work and I'm dead as tired.